This is Jason McIntosh with McIntosh Applied Engineering. In this video, I'm going to show you how to use the Sonion and Knowles elements for speakers and microphones. We're going to start out by creating a new modeler module. The new elements are in the acoustical menu. Here are the Knowles and Sonion speaker elements. These elements are mostly balanced armature devices, which are also known in the hearing aid industry as receivers. So I'm going to go ahead and create a Knowles element here. When you create the element, its parameters in the params tab appear on the left of the screen. Right now, there's only one Knowles device listed in the library. We'll be adding more as time goes on, but we want to get this Pro Audio device out as soon as we could. So to connect to this and start driving it, we're going to need a voltage source. Aries now has AC and DC voltage sources. Some of the new devices that have been added, including these MOSFET devices down here, required an iterative DC solver, so now we need DC sources. But to do a frequency analysis, we want an AC source to drive our speaker with. That source needs a ground reference, so we're going to go ahead and create a ground element to go with it. We're going to connect that up to the electrical terminals of the speaker element, and we want to load this down with, in this case, ear simulator. Now the ear simulator has three connectors on it. The red connector is the one that you want to acoustically drive. It represents the ERP point for the simulator, known as ear reference position. The node on the right, it's blue, it's a listening node. That represents the response that you'll get from the microphone inside of your ear simulator. And the node to the lower left is diffuse field correction pressure. So this is the equivalent diffuse field pressure that will generate the ERP pressure that we're going to get from our model. In general, these receivers are used in insert headphones and hearing aids. For headphones, you usually want to design it to have a flat diffuse field response. So this node here is going to be important for that. So we've hooked up our model, and I'm going to go ahead and press Calculate. Okay, the model's run. I'm going to create a graph element. And I'm going to go ahead and connect it to this diffuse field connection node. Here's the graph window that was created when we created the graph element. As you can see, it's relatively flat as it is already. Some of these peaks are due to the natural resonances of the balanced armature receiver, but we see we have a big null here at about 5 kilohertz, just about 5 kilohertz. It's worthwhile to understand where this null is coming from when you build a model, so I'm going to step off and take a look at that real quick. To show where it comes from, I'm going to create another graph element, and I'm going to connect it up to the loading point on the ear simulator. And something I forgot I wanted to do was I wanted to change this ear simulator type to a 711. This is an ITU type 2. This represents just an ear canal. I had it on the sealed ear simulator, but I want to change it to the 711 and rerun our model here. So again, we see we have a big dip at a little above 5 kilohertz. We're going to see that this is due to the resonance of the ear canal. This element here is currently graphing pressure. I want to change it to impedance. This is the graph that was created when that second graph element was put in the model. What you see here is the acoustical impedance magnitude in dB of that 711 ear simulator, and it has a big drop in its response at a little over 5 kilohertz. This is a very difficult load for that receiver to drive, and so it doesn't generate much pressure at 5 kilohertz. And this is the reason for the minimum in our frequency response here. So if we're going to try to design a flat response using this receiver, we want to keep in mind that our biggest deviation from a flat response is coming from this really low impedance with the ear simulator. So that's an important thing to keep in mind as you do this design. There's also a Sonion receiver. When you create that, it's the Sonion models that are available for modeling appear in this list box. There are quite a few here. The Sonion models are a little easier to deal with than the Knowles at this point, so they're already present in Aries. These models are contained in this new file that comes with the Aries distribution lists. It's called the vendor component library file, and as we add more components, this will get updated. You use the Sonion element the same as the Knowles. I'm going to go ahead and duplicate these electrical elements to make it easy to hook them up to the Sonion device. I'm going to duplicate that ear simulator as well. Run this model. So I'm going to copy the current response into a buffer labeled Knowles, plot it, and I'm going to go ahead and connect to the ear simulator that the Sonion device is running. So what we have here is the Knowles response in green, and the current buffer is the Sonion response in blue, and you can tell that they're pretty similar. There's some differences due to the internal resonance structure of the two devices, but they both suffer from this big drop at 5 kilohertz. So they're going to end up with relatively similar designs once you're done equalizing this. Okay, I'm going to go on to the microphone elements now. I'm going to go ahead and create a new modeler module. Pull down, and I'm going to go to this Knowles Omni microphone. To get some output from this device, I need to drive it, so I'm going to create a acoustical pressure source to excite it. I want to look at the electrical output, so I need to put a reference on this negative terminal here. If you don't have a voltage reference somewhere, it doesn't know where to place the absolute voltage, so I need to put one at ground. I'm going to go ahead and put a graph element on and hit calculate. This is the graph that was generated, the graph window that was generated. It's hard to see how flat this is. We're kind of got magnified view here, and it's everything shifted down to the relative sensitivity of the microphone at -38. So I want to shift this up to 0 dB in the midband so I can see how much we're deviating at the low and high frequencies. One way I generally do that is to go to the pressure source and just add 38 dB to the pressure source and recalculate. Now when we go back to the graph, the microphone response is centered around 0 dB volts in this case. And you can see that our low frequency limit down around 100 Hertz is off not quite 3 dB from the mid-band level. And at high frequencies, we're up about 1 dB at 10 kilohertz. So that's not too bad. If we click on that and we pull down its list of devices again, we only see one. This is a commercial grade MEMS microphone from Knowles. And again, we'll be adding more devices soon. If you don't see the device that you want to model, please contact McIntosh Applied Engineering, and we'll do our best to include that in the vendor component library for you so you can start using that. So I'm going to go ahead and create a Sonion microphone. These are a little different. They have a power connector on them, power connector node. This allows you to set the bias point for the internal MOSFETs in these Sonion models. Sonion models are pretty sophisticated, and we're taking advantage of that, and we'll be able to see how much power these microphones use. So again, I'm going to create a pressure element to drive it. I want a ground element to reference the voltage with. And now I need to power that with a DC voltage source. If you're not sure about the element, right-click on it, pull up Help. Here it'll say for the Sonion microphone, and a dialog box will pop up, and it'll tell you what the element is about and what the parameters are for. So I'm going to go ahead and create a DC voltage source now. By default, this has a voltage of 1 volt. I'm going to go ahead and change it to 2. I'm going to ground it down here. These devices will typically run off of 1 volt, but I'm going to bring it up to 2. I'm going to hit calculate. So when I hit calculate, we got this error here. These things can be tricky. Turns out in this case, the error is coming because we're driving this input too much, and the circuit here isn't able to converge. So we're actually driving it at about 140 dB, which is a bit too much. If I drop this down to 94, this rather sophisticated Sonion model is able to solve at that point. Everything's properly biased inside. Let me pull down this graph, connect it up to the element, and we see that we've got a nice response here from it. These hearing aid devices typically have a resonance up around 6-7 kilohertz, and then they don't have much of a response after that. It's because the most hearing loss is so severe at high frequencies that there's not a lot of reason to correct for it, and also the feedback cancelers have a hard time with these higher frequencies. So the hearing aids generally only go up to about 6 kilohertz or so. Again, we'd like to see this centered around 0 dB, but we've seen that if we add too much pressure to this source here, it'll cause some problems with our modeling. So instead of adding 30, what do we need here? About 33 dB. Instead of adding that to the pressure source, I'm just going to put a voltage amplifier in here. Put a voltage amplifier in our circuit. I'm going to set its gain to be 33 dB, recalculate, and now the response is centered roughly around 0 dB. So we can see we've got about a 5 dB rise at high frequencies and about a 10 dB drop down at 100 hertz. So it's far from a flat response, but it's still a useful device. With the new DC solver that this Sonion element is using, there's the ability to see what the DC values are at the various nodes for the element. Whether these are displayed or not is controlled with the options menu. There's an option now for display DC solution. So if I turn that off, the DC values disappear. Turn that back on, they come back. Which node number corresponds to the node on the element, you're going to have to kind of figure that out. These don't have labels right now. So we know that the power node is at 2 volts, and that's node 4 here at 2 volts. And right now it's consuming about 97 microamps, so we can see how much power that element is consuming. Well, this is all I wanted to cover with this video. You've seen the new Knowles and Sonion microphone and speaker elements. Again, if there are some devices that's not in the library right now, please contact us. We'll do our best to get that to you as soon as possible. I want to thank you for your time and hope you continue to enjoy using May products.